So let me share my screen first. Right. So okay, we have reached the chapter 7. So previously I have explained about MIPS or instruction language of the computer, right? So today, okay, I would explain about the instruction representation. So whatever that we have learned last time, okay, you would need to understand what does the instruction represent to the computer itself, and then to the user on a higher level language. Okay, so sometimes I would use like a C++ example to explain what does the instructions entails to, right? So okay, so first is that I would explain about the instruction representation based on these three formats, so R, I, and J. So today, you will learn how to decode, okay, a MIPS code to a machine instruction, okay, using these three format. Okay, so you need to have, you need to open your green sheet, okay, MIPS green sheet. Where is it? This one. Okay, so this one you would need this together with the slides. Okay, so for you to learn how to represent it, right? Okay, first is that the abstraction or the level of representations, okay, in your programming or in your computers. Hold on, okay. So first is that you have learned about high-level language, right? For example, in C++, or maybe Java, or PHP. And then you would load your programs, okay, to the IDE. Okay, so within that IDE, they have a compiler. Okay, they have a C compiler, Java compiler, and other language compilers. So each of these language have their own compiler. And then, okay, so these compilers, okay, would change or represent it to an object module, or in this case, the assembly language program. Okay, so for example, we have a MIPS. So under this MIPS or under this assembly language program, okay, they would load into the assembler. Okay, so the assembler would create the executable code. Okay, so the executable code. So but actually, okay, within that executable code, they have a machine language program. Okay, so this machine language program, okay, can be executed. Okay, can be executed so that, okay, it can we can run to the processor. Okay, we can run it to the processor. So within the executable, okay, it contain a machine language program whereby it was interpreted into a machine instruction. So here, okay, first is that this is your coding in C++, okay, and then we change it, okay, the compiler change it to as an assembly language program. Okay, so here this assembly language program is converted or is assembled to a machine language program. So in this case, because a machine can only understand binary numbers, so this code, okay, assembly code, okay, is assembled to a machine language. Okay, so as you can see, okay, we just can treat this one line of 32 bits, 32 bits binary numbers as assembly code. Okay, so we can consider this is load word T0, 0, and then S2, like that. Okay, so each of this line is an assembly code that needs to be executed. Okay, so once they have decode to assembly code, okay, so this number would be fit into the hardware architecture description or to the block diagram. So in this case, to our processor. So within the processor, they would decode the machine instruction, and then read the content of the register, and then execute the operation based on this machine instruction. Okay, and then the ALU would be implemented. Okay, so within this ALU, actually it's a combination and also sequential circuit. Okay, so this is the lowest level of the machine. Okay, so we are not going to deal about this because we have covered this part. But okay, this time, okay, so chapter 7 until chapter 9, okay, you will learn about this part. Okay, assembly language, program, machine language, and also the hardware architecture. Okay, the hardware architecture. So the big idea. Okay, the big idea. I would explain about the big idea of the instruction representation. Okay, so we treat the instruction as a numbers, and also we encode the instruction. And then I would explain about the MIPS instruction format for add instruction, and also other instruction format for immediate data transfer instructions. Okay, so all types of instruction would be covered on these chapters. So we have 45 slides, so I need to finish it within these 2 hours. Okay, right. So we treat. Okay, we would like to treat. Okay, so the big idea of the instruction representation is that we treat the stored program concept as a memory. Okay, so remember that computers built on 2 key principles. So the instruction are represented as bit patterns. Okay, so we can think that this instruction as numbers. Remember, because the computer can only understand bits, so we can represent the instruction as numbers, okay, in bits. Therefore, the entire program can be stored in memory, okay, to be read or written, just like data. So all data, all instruction, okay, can be represented into a bit patterns, whereby these bit pattern can be stored in memory to be read or written. So this would simplify the software and hardware of the computer system. Okay, because of the memory technology for data can also be used for the program execution. Okay, so what are the consequences? Okay, everything is addressed. Okay, everything are addressed, meaning everything can be retrieved or stored, okay, based on address. So since all instructions and data are stored in memory, okay, remember from the hard disk, okay, we take out the program and then send it to the RAM, okay, so to be stored in a block like that. And then when we want to execute the program, so we take out certain blocks and then put it inside a cache, and then from that cache we decode it. Okay, so everything is stored in a memory. Then everything has a memory address. So this includes instructions and data words. So within the memory, so one type, okay, so within the cache memory, we can divide it into one is instruction, and then one is data. So whatever data that we want to process, everything will be loaded into this one portion. And then for the instruction, they will load it into instruction memory. Right? So also branches and jump would also use the memory address. So there are certain instruction that would use a memory address. Okay. If you learn, okay, if you learn, you are not, I'm not sure if you have learned about C pointers, but this chapter of C pointers is actually at the end of the course actually. Okay, so C pointers is actually on maybe week 12 or 13. Okay, so but I'll just raise it on this topic. So the pointers are just a memory address. Actually, they are saving the memory address into the pointers so that they can point to anything in memory. Okay. Unconstrained use of addresses can lead to a nasty bugs. Okay, in C, okay, it depends on the programmer. Okay, whereas in Java, they will be limited. Okay, they would limit it the usage of addresses. Okay, so one register can keep the address of instruction being executed. So last time or the last session of the lab, I have told you about the program counter, right? So this program counter, or what I call as PC. Okay, so there is a lot of abbreviation that is used during our assembly and also on this course, right? So in this case, PC here is considered as program counter. Okay, um, so basically a pointer to memory. So this PC would point to a memory. So they would pick up the memory address and then point it. Okay, point it to the memory. So the Intel processor would call it instruction address pointer. Okay, so as a better name so that the other or programmer can understand it. So actually it's an instruction address pointer, right? So the programs are distributed in a binary form. Okay, treat when we treat instruction, we treat the memory address as an address. Okay, so everything is in a binary form. The program are bound to specific instruction set because we are using a binary form, right? So we must have a certain set that needs to be set up, okay, for that program can be executed. So for a different operating system or different processor family. Processor family. Okay. So for a different processor families, they have a different version. So for Macintosh, they have a different version of binary form. And then for Intel, they have a different binary forms. So these new machines, okay, wants to run all programs which is the binaries as well as programs that are compiled to new instruction. So remember, first is that C, and then the next version is that they have a C++. They improve it, right? But the C++ should be able to run the C programs. Okay, so it's a backward compatible. So this leads to a backward compatible instruction set evolving over the time. So that's why the selection of Intel 8086 in 1981 for first IBM PC is a major reason the latest PC is still using the 8086 instruction set. Okay. So basically, the assembly language of 8086, okay, is still used, okay, for the latest version of the assembly language. Okay. So they use the versions of Pentium 4 8086, whereby it can still be run, okay, from 1981 PCs, okay, until today. So that is the major versions of why they use the assembly 8086. Okay, so the previous one, the VEX, those things are not popular anymore. Okay, so Intel 8086 is much used, okay, by the computers, right? So currently all data that we work with is in words. Okay. So one words mean one block. One words is equal to one block and is equal to 32 bit of data. Okay. So each register is a word. So the size of each register. Okay. Size of T0 is 32 bit. Okay. If you open, okay, if you open your macam mana saya nak buka how do I open it? Kat sini. Let me search QtSpim. This one So let's say I'm opening my QtSpim And then when you look at the registers here, sometimes they have a number, right? So you just convert it into binary. Okay, just convert it to binary. You can count the number. It's always 32. So each registers can store 32 bits data. Okay, 32 bits binary data. Okay, so let me close down. Right, so load word and store word both will access the memory one word at a time. Okay, so remember the command of a load word and store word is load means to retrieve data from the memory. So what they retrieve is that one word. And also for the store word also the same. Store word means to store one word to the memory. So how do we represent instruction? So remember, computer only understand 1 and 0, binary only, right? So if we write add T0, register 0, and then register 0 is meaningless to the machine itself. So we need to represent it into binary. Okay, so MIPS want simplicity. Since data is in words, so we mix instruction to become words too. Okay, so let's say one word is 32 bits. So we would divide the instruction word into fields. Okay, so to represent what are the opcodes, what are the registers needed, and what are the labels or maybe address that we need to retrieve. Okay, so each field here would tell the processor something about the instruction. Okay, so we could define these different fields for each instruction, but MIPS is based on simplicity. So they just define three basic type of instruction format. So we have R format, I format, and also J format. Right. So instruction format, okay, is would be used during the machine decode. Okay, when we decode the machine, so they would use based on this format. So I format is used for instructions with immediate. The word I here means immediate. I here is immediate. And then also used for load word and also store word, since offset counts as an immediate. Remember when I type load word register T0 16 and then register as 0, right? So 16 here is an offset, and offset is also considered as immediate. Okay, and then we also consider branch. Okay, branching means if. Okay, if then else. Like that. So we are using branches. So branches is considered as I format. Okay, but not the shift instruction. So shift instruction was not considered as SI format. So shift is considered as R format actually. Okay, and then J format. J format is used for instruction J and also JAL. So only two instructions is under the J format. And then R format is used for all other instructions after the I format and J format. So whatever that is I format and J format, apart from that, that is for R format. So it will soon become clear why the instructions have been partitioned in this way. So the R format. Okay, so how do we want to know that? So remember when I said about the MIPS screen sheet. So this is like your cheat sheet, you know. So your cheat sheet. So I would open it, this one. And then you can just scroll down on the first page. It was at the bottom of the left page. Okay, it was on the bottom of the left column, left column. So here you can see basic instruction format. We have R, I, and J. So basically, this is like a cheat sheet for you to look into. Okay, so if it's a face-to-face or in a written exam, actually during the final exam, they would give this to you. Okay, so how do you want to know if the instruction is an R, I, or J format? Look at the left column here. Okay, which is this is for 32 bits. Okay, for a decimal. Okay, for normal numbers, not to look at the right one. Okay, don't look at the right one. Okay, so look at the left one. So as you can see, ADD is R format. Okay, and then we have an opcode and function here. So you would see this part later on. Okay, what about load word? Load word, okay, is I format. Okay, and then this is the opcode numbers. Right. So this is how you want to read the green sheet. So I would tell you later on how to look back on this part. So let me drag this on the other side. All right. So look back at the R format. Okay, so R format defines fields of the following number of bits, where each field, okay, so the first field is 6 bit, this is 5 bit, 5 bit, 5 bit, 5 bit, and then the last one is 6 bit. So if you count, okay, if you add everything, you would get 32 bit. Okay, so this is the size of the field itself. Okay, so for simplicity, each field has a name. Okay, they have opcode, RS, RT, RD, shift amount. As sham here means shift amount. Okay, shift amount. Okay, and then function. Okay, so the last one is a function. So basically, it's the same as an opcode. So that's why the size is 6 bit. So important, on these slides and in book, each field is viewed as a 5 or 6 bit unsigned integer. It's unsigned integer, not as part of a 32 bit integer. So the consequence is that the 5 bit fields can represent any number from 0 to 31. Thus, where does it come from? The number of the registers. Okay. So we have the number of registers from 0 to 31, right? So we have 32 registers. Okay, 32 registers in the MIPS. Okay, so 32-bit registers, and it was represented in 2/5, means 5 bits. Okay, to represent these registers. So RS, RT, and RD is a field for registers. Okay, and then while 6-bit fields can represent any number from 0 to 63. So value can only from within this range, 0 to 63, for the opcode and also function. Okay, so if you have a question, I may not be able to see it, guys. So you must unmute yourself, to talk to me. Right. So right. Let me continue. Okay. So what do this field integer value tells us? Okay. So for field opcode, go back. So for field opcode here, it partially specifies what instruction it is. So know that this number is equal to 0 for all R format instruction. So for R format instruction, the opcode is always 0000000, like that. Okay, and then for function, it combined with opcode. Okay, combined with opcode, so function is 6 bit, right? So this number exactly specifies the instructions. So only on function field does the value has a bit 1. Okay, they have a value bit 1 to indicate, okay, to indicate that this is an R format. This is an R format. Okay, so why on opcode and function is combined into a single 12-bit field? Okay, because of the I format and also J format. Okay, so they only use opcode. They are not using the function. Okay, the function field would not be used later on. So that's why they just use opcode. They separate the opcode and also the function. Okay, so actually when I said we'll answer this later, it's because of I need to explain about I and J, so then you will be able to understand why opcode and function is not combined into 12-bit field. Right. So next is the registers. We have source registers. RS means source registers. Generally used to specify register containing the first operand. So let's say if I write ADD register as 0, comma, register T0, comma, register T1. So in this case, the second one is the source register. Okay, this second one is the RS. So source here means all the value that we need to add. Okay, we retrieve from this source register. Okay, so and then we have a target register. Okay, you have a target register, generally used to specify register containing the second operand. Okay, so if RS contain the first operand, okay, or the first value that we need to do the operation, so the second one is the RT here is the register that contain the second operand, okay, or second value. So note that name is misleading because RT here can be a target. Okay, RT here can be a target. So like this, okay, you will see later the usage of this RT. Okay, so RT can be a source and also RT can be a destination register. Okay, so you will see it later on. But look at the R format only. Okay, only for R format, we have two source, RS and RT. Okay, so RS plus RT, we would save it in RT. Like that. So I can also show you on the QT SPIM here. On the green sheet. Look at the operation. Okay, on ADD, it says here RD is equal to RS plus RT, as I mentioned before. See? So that's how you want to read the green sheet. Okay. So next is that register destination. So this is where the destination or the result will be stored into. Okay. So D means destination. So notes about the register field. Each register field is exactly 5 bits, which means that it can specify any unsigned integer in the range of 0 to 31. Each of these fields specifies one of the 32 registers by number. So that's why when you want to refer to the green sheet, you always look at the number. This one, number column 0 until 31, because you would use this number to convert to a machine code. Okay, to convert to machine code. So, each of these fields will specify one of the 32 registers by number. So, the word generally was used because there are exceptions that we would see later on. Okay, for example, multiplication and division. Okay, multiplying and division have nothing important in the RD field since the destination registers are high and low. Okay, so move from high and move from low have nothing important in the RS and RT fields since the source is determined by the instructions. So remember, when we try to use a multiplication and division, we would use these two registers, high and low, as your destination registers. Okay, so where is the command for multiplication? So it was not on the left column. It is on the right column here. Multiply, MULT. And then RS multiply by RT. So the result will be saved into these two registers, high and low. So do remember, when we multiply, we double the size. Okay, we increase the size. So maybe the bits would increase. So if we multiply 32-bit registers to 32-bit registers, so it would exceed, the value would exceed more than 32 bits. So that's why we need high and low. So two registers, okay, to be used. And then another command that we would use for our arithmetic, only these two, division. Okay, so you would use division to divide. Okay, also again, they are using low and high registers. Okay, to store your result. To store your result. Right. What else? What else? Here, move. Okay. MFHI, MFLO. So MFHI is a move from high. And then MF low is move from low. So we want to move the high and low register to the destination. So you can use this command, okay, to move the content of the result of the multiplication or division. Okay. So right, the final field is the shift amount. Sometimes students like to say sham. Okay, whatever it is. But just remember what is sham. It's a shift amount. The amount that a shift instruction will shift by. So there is an instruction whereby, let's say you are writing like this, 1 1 0 0 0. So when you want to shift to the left, okay, shift left 1 bit. So if you shift left 1 bit, so you move this dot to the left, so it would become 1 1 0 0, just like that. Okay, so this is the number of bit that we need to shift would be stored into this shift amount. Okay, but the shift amount only have 5 bits, right? So shifting can be done only for 5 bits only. Okay, so shifting a 32-bit words by more than 31 is useless. Okay, so they can only shift for 31 bits only. 31 bits only. So this field is only 5 bits so that it can represent 0 to 31. So let's say if I want you to shift to 16 bit. So 16 in binary is 1 0 0 0. So still it can be stored into the shift amount because we only require 5 bits, right? So the maximum is only 5 bits. Okay, 1 2 3 4 5. So if we put a 1 1 1 1 1 means that only 31 bits can be shifted. So this field is set to 0 in all other instruction except the shift instruction. So let's say if you are using, if you need to decode ADD, register T0, register T1, register T2. So within the column of shift amount, because we are not doing a shifting instruction, so shift amount contain a 0 bit. Contain 0 bit. Right. So now we are going to decode the instruction. So let's say you are given a MIPS instruction. You need to decode this instruction into a machine code. Okay, decode to a machine code. Okay, so now you are becoming Neo in matrix. Okay, Neo in matrix. So, okay, so the arrow here means decode. So now, determine what type of the format for this instruction. Look at the format. Okay, so look at the format. Okay, so if you look at the format, ADD, mana ADD? Where is ADD? Is R format. So if it's an R format, go down. Look at the how many columns that we have, how many fields that we have. Opcode, RS, RT, RD, shift amount, and then function. So you need to fill in that part. Okay, you need to fill in that part. Okay, so we have 6 fields. So opcode is 0. Okay, so how do we know the opcode is 0 or not? Look at the column opcode / function there. Okay, so they are telling you the first left is the value for the opcode, which is 0 for add. And then for function, it is 20 hex. Okay, 20 hex. So you can see on this opcode, okay, on this opcode, on this R format for add, opcode is 0 and then function is 20 hex. Okay, I've written it in decimal on this slide. Sorry. All right. Okay, so basically 20 or 32 is the same. So how do I know that? Go back to the second page. So 20 hex. Look at hexadecimal 20 here. You can see 20 in hex is basically 32 in decimal. Sorry. Hold on. All right. Okay, next is the RD. So the position, okay, the position in the in R format, okay, for the instruction here. Okay, usually the left one, okay, the left one would be the destination. Only it depends on the field itself. So depends on the instruction. So because ADD require two source registers and one destination registers, then this one become RD. This one become opcode. This one become RS. And then this one become RT. So 9 here, register 9 is your first or your source register. Register 10 here is your target register. Okay, or your second source register. So they don't want to write second source register because this name will be used later on. So they use the RT. Okay, so if you look here, RD is 8, RS is 9, which is the first operand. RT is 10, which is the second operand. But we have another field sham, right? Or shift amount. Because this is not a shift. Okay, this is not a shift instruction. So we put a 0 there. You will put a 0. Okay, next. So now you have the composition, right? So you have the composition. Oh, so what is the opcode function and everything? So you would put this number into the field. Put a number. Okay, so opcode is 0. Function is 32. Okay, function is 32. Or maybe you can write 20 hex. So why am I not writing it 20 hex? It's because of I'm represent it using a decimal number. But if you prefer to use the hex because later on you need to convert it into binary, then do so. You can do that. Okay, but provided you remember this is a hex. So that's why during if I'm writing this, I would always write 20 hex, 20 hex, 20 hex. So that I would remember. So if there is an hexadecimal, then I need to convert into from hexadecimal to binary. Like that. Right. Okay, and then the first field is the RS, and then this one is RT, and then this is RD. So how do I know that? Look back at the basic instruction format. We have RS, and then the second field is RT, and then the third field is the RD. Okay. So we do know this is function. Okay, this is RD, this is RS, this is RT. Okay, but the formatting of the MIPS format for R format, is opcode RS, RT, RD. And then this is shift amount. So you need to rearrange back again. Rearrange. So now you will put up, okay, the value for each of these field. Function is 32 or 20 hex. And then your opcode, since this is R format, so opcode is always 0. And then your RS is your 9, RT is 10, and then RD is 8, your shift amount is 0. And then convert this number into binary. So based on the size of each field. Remember the size of each field. Opcode is 6, function is 6, the rest is 5, 5, 5, 5. So 0 is converted into 6-bit 0, and then 9 is converted into 01001. So don't forget to put a 0 at the front of it. Okay, so to complete the 5 bits. And then the next one is 10, is also the same, 5 bits. So they become 01010. And then 8 becomes 01000. And then for shift amount, 5 bit 0. And then last one is the function. So function is 32. So you can also use your calculator to convert 32 to binary in 6 bit. The size is in 6 bit, okay? So for hexadecimal, you can convert this to 4-bit binary, and then this one is to 2-bit binary. So you will get 000 and then 10 for your function. And then combine all. Okay, you combine all. Divide it into 4 bits, right? So you divide it into 4 bits like this, like this, like this. Okay, like this. Okay, so you combine it. Okay, so you need to combine it later on. Like this. Okay, make it, divide it into 4 bits. So what will you get is this is 0, this is 1, this is 0010 is 2, 1010 is A, 0100 is 4, this is 0, this is 2, this is 0. So when you combine later on, you will get 012A 4020. So this is your machine instruction. Okay. So if we expand it, it will become like this. But if we simplify it, it will become a hex machine instruction. So in decimal representation, we can use the calculator. You can use a calculator to represent this machine instruction in hexadecimal to decimal. Okay, so this number and also this number in hex is what we call as the machine language instructions. Okay, so if you successfully convert it into a machine instruction, congratulations, you are able to decode your machine instruction. Right? So I format. So I format. What about the I format? So I format is about immediates. Okay, if I say I means immediates. So what is immediate? It's a 5-bit field, only represents number up to the value 31. So immediates may be larger than this. Okay, so if let's say we want to use the shift amount for your immediates, it does not, it can only represent until 31. But actually, it should be larger than this. So ideally, MIPS would have only one instruction format for simplicity. Unfortunately, we need to compromise. Okay, so they define a new instruction format that is partially consistent with the R format. So first, notice that if instruction has immediate, then it can only use at most 2 registers in the command. So look at the I format instruction. They have only 4 fields. So one is the opcode. Okay, 6 bit. It's always 6 bit. RS and RT is also the same. 5 bit, 5 bit. So you can just write here 6, 5, 5. So at the moment you only have 5 plus 5 is 10. 10 plus 6 is 16. So the rest. So your RD, your shift amount, your function would be combined to become immediate, which is the size of 16. So if you have a 16 bit, means that 2 power of 16 value. Okay, 2 power of 16 value. So the key concept is that only one field is inconsistent with the R format. Okay, so most importantly, opcode is always in the same location. So that's why we did not combine opcode and function in the R format because of this reason. Okay, because there is a changes on the field, so only opcode remain. So that's why opcode always 6 bit. Okay, so next is that what are the fields mean? Opcode is the same. Since there is no function field like R format, so opcode uniquely specifies an instruction in R format. So this also answers questions of why R format has 2 6-bit fields to identify instruction instead of a single 12-bit field. So in order to be consistent as possible with other formats while leaving as much space as possible for the immediate field, because we want to store as much as possible to put a value, a constant on this immediate field. RS is the same. So specifies a register operand if there is one. Okay, sometimes there is no value in the RS. Okay, and then RT specify register which will receive result of computation. So this is why it's called the target register or other operands for some instructions. So in this case, RT become the destination. Okay, so RT become destination, but they did not use the destination for the other format, I format and J format. Okay, it's because of they are using the target. Okay, why they keep on using the target register in the I format, right? Okay, so immediate field. Okay, the instruction immediate field, sometimes they have I at the back of it. So ADDI, SLTI, set less than immediate unsigned. So this immediate is a sign extended to 30-bit. So previously the immediate field is 16-bit, right? So when they execute into the processor, okay, this 16-bit would be extended, sign extend to 32-bit data. Okay, so sign extended. Okay, so they would extend this 16-bit to become a 32 bits. Thus, it's treated as a signed integer. Okay, so let's say if you have 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. So this is 1, 1, 1, 1, then 1, 1, 1, 1. So 1, 2, 3, 4, 5, 5, 6, 7, 8. Okay. So sorry, it's not like this. So 1, 2, 3, 4. 4 times 4 is 16, right? So let me correct back again. So let's say this is your immediate value. So let's say this is your immediate value. So when they sign extend, they would extend the first sign bit here. So they would extend to become 0, 0, 0, 16 bit more, like that. Okay, so 1, 2, 3, 4, like that. So this is what we call as sign extend. Okay, so 16 bits can be used to represent immediate up to 2 power of 16 different values. This is large enough to handle the offset in a typical load word and store word, plus a vast majority of values that will be used in the SLTI instruction. So SLTI is like if I is less than 50 or maybe 100, like that. So we can also use the SLTI instruction. So we will see what to do when the number is too big in our next lecture. So at the moment, it can only handle up to 2 power of 16 values. Right, so let's decode. First, okay, let's look at the command. ADDI, register 21, register 22, and then minus 50. Remember, when you use an I format like ADDI, the number can be a positive or negative. So you must retain the sign bit. Okay, look back at the green sheet. What is ADDI format? And then look at ADDI. It's there, ADDI. So if you cannot find it, you can just Control F and then find ADDI. There, there. So it shows, it highlight the ADDI here. So as you can see, it is an I format. And then the opcode is 8 hex. Opcode is 8 hex. So here you would write opcode is equal to 8. And then RS, this is RT. This is RS. Okay. 22 here is your source. you need to add with the negative 50, right? And then store it into register 21. So this is your target. So your RT is 21, RT is your, RS is your source containing the operand. And then your immediate is negative 50. So by default, this is decimal. Okay, by default, this is a decimal. So only ADDI can accept, only the command that has an I can accept a negative numbers. Right. If instruction, ADDI. So let's write back again. This is opcode. This is RS. 22 is RS. 21 is RT. And then this is immediate. Always do it like this. And then, okay, put it inside the field. Okay, so this is opcode of 6 bit. This is 5 bits of R. Can't remember. Look back down. Okay, so this is RS. Okay, so this is RS there. So this is RS. Where's my pen? Okay, RS in 5 bit. RT in 5 bit. And then this is immediate in 16 bit. So you put it back, the value that we have determined, opcode is 8. And then RS is 22. And then RT is 21. And then your immediate is negative 50. And then use your calculator to convert your value, decimal value into into binary. Binary. So convert into binary. So 8 is 001000 and then 22 is 10110, which is 5 bits. So you must complete it to become the size of that field. Okay, so let's say 8. 8 is only 1000, but since this opcode must have 6 bit, right? So you must extend it. Okay, add a padding 00 to complete the 6 bit. Okay, it's also the same for 21, 10101. And then for negative 50, this is a sign bit of negative, right? So make sure, okay, so the value of 50 and then with a sign extended until 16 bit. So I would count how many bits that you have on your immediate. Okay, I will count it. Okay, so please make it easier for me to read. So you separate the 4 bit so that you would not make a mistakes. Alright. So once you have decode into a binary, then you can also represent it into hexadecimal. Okay. Tak ada pula kotak. Right. So this is your answer. Okay. So this is your answer. Next is that, okay, so problem, unsigned sign extended. Okay, so there is a certain problem. So the first problem is that unsigned sign extended. So ADDIU, okay, add immediate unsigned dengan and set less than immediate unsigned. Okay, means that we sign extend the immediate to 32 bits. Thus it becomes a signed integer. So let's say your number is 0, then 111, and then 112, 1, 2, 3, 4, 1, 2, 3, 4. So when you sign extend, so to become a 32 bit, okay, to become a 32 bit, so what happened is that this is a sign bit. This is a sign bit, So this is a sign bit integer. So the rationale is that ADDIU or add-IUs can add without overflow. Okay, using the unsigned here. Okay, using the unsigned, they can ignore the overflow of the bits. Okay, set less than immediate, unsigned suffers so that we can have easy hardware. So does this mean that we will get a wrong answer because we ignore the unsigned, right? So no, it means assembler has to handle any unsigned immediate to power of 15 because the left bit here, so the 16 bit here is used for assign, right? And then between 2 power of 15 to 2 power of 16 with a 1 in the 15 bit and 0 in the upper 2 byte. So as it does for the numbers that are too large. Okay, so another problem is that chances are that ADDI, load word, store word, and SLTI will use immediates small enough to fit in the immediate field, in this case 16-bit. Okay, so we consider that the immediate number can fit into the 16 bits immediate field. But what if we need to operate a big data? Okay, a big data. So what if it's too big? So we need a way to deal with a 32-bit immediate in any I format instruction. So the solution to the problem is that we can handle it in software plus new instructions. Don't change the current instructions. Instead, add a new instruction to help out. Okay, so do remember when we add I like that, register T0 and then register 0 like this, and then you want to add like number what number 32. Okay, 32, let's say like this. So the 32 will be in 16 bits, right? So 16 bits, so 0000 and 0 01 00 and then 00000000 like that. So it will be on the lower half of the registers. Okay, it will be on the lower half of the registers. So the upper half here was not used. Okay, so was not used. So let's say if you want to use the whole 32 bits, then we cannot use the add I here. So instead we use a new instruction called load upper immediate. Okay, load upper immediate, register immediate. So it means that it stands for load upper immediate, LUI. Okay, so it takes 16-bit immediate and then puts these bits in the upper half. So when you use the command LUI here, so the value 61 will be put on the left side one. So the upper side. Okay, the upper half or the high order half. So this is high order half. This is low order half. So always when we use the add I or maybe SLTI, so they always put it inside under low half. Okay, but if you are using a load upper immediate, then they would load that data or the number or constant to the high order half. And then for the low order half, okay, for the low half here, they would set it all 0. So all 0, they will become all 0 on the low order half. Right. So how does LUI help us? Okay, so how does LUI help us? For example, the first function for LUI is that to store memory address pointer. This one was not written in the slide, right? Okay, please write it on your notes. To store memory address pointer to register base. Okay. For example, before you want to load word, okay, whatever lah. Load word register T0, maybe 16, and then register S7. Remember the exercises, right? So S7 is the register base, right? So before you want to use the load word, you must load the memory address pointer to the S7. So how do you want to use that? Okay, so you can use the LUI command. Okay, so that is one. And then also, LUI also can copy 16-bit constant to the left 16 bits or high order half of the 32-bit registers. And then it can clear write 16-bit or the lower half here of the 32-bit registers to 0. And then use the OR immediate to combine the 16 high bits and 16 low bits into a giant 32-bit number. For example, when you want to ADDI T0, T0, 0x, AB, 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 CD, CD, CD. So basically, ADDI can only take 16-bit or 4 hexadecimal numbers. Okay, so only 4 hexadecimal. So if you write it like this, it become an error. So you can only take 4 only. Macam tu, like that. Then, so how do we want to store ABAB CDCD? So first is that use the command LUI and then register AT and then 0xABAB. Or you can just write register T0 like that. No problem. Okay, no problem. T0 So use register T0 to store 0xABAB on the upper half. Okay, on the upper half of the register T0. So there would be data of ABAB on the upper half and then 16-bit zeros on the lower half. Next is that you use a command OR immediate, okay, to add the previous register here 80, right? So this the last result, okay, would be used as the as the source. Okay, 80 here is used as a source for the next or immediate instruction. So 80 plus, okay, plus CD CD. Okay, 80 plus CD CD. You will store the CD or the data, the integer that you want to, the hexadecimal number that you want to store on the lower half. But what about the upper half? They don't change it. Okay, they don't even disturb it. So they won't affect anything. So now we can combine it. Okay, now we can combine it. So to become a full 32-bit data. Okay, here they use 8080 to save it into an 80 registers and then 80 plus T0 store back to the T0. So basically you can just skip this part. You can just use T0 here. T0 and then T0 here and then T0 just to skip that part. Okay, so now you only have 2 instructions to store these 32-bit numbers. Okay. Right. Next is the branches. Branches is what we call as a PC relative addressing. Why we call it PC relative? It depends on the number of instructions. So that's why it's relative to the instruction that is stored by the PC. So that's why we call it relative, PC relative addressing. Alright, so branches still use I format. Okay, so the opcode will specify BEQ or BNE as I format. So what is the opcode for branch is, you can just look at the green sheet here. BEQ is 4 hex, BNE is 5 hex. And then if we want to write it, say here, branch on equal is if RS is equal to RT. Let me open a notepad. Where's my paint? My paint. Hold on. Okay. So, so branch equal is that if, okay, we can write it like this. If RS is equal to RT. Okay, so if RS is equal to RT, so where do we want to go? So it says here, if it's true, we can jump to the branch address. So if it's true, okay, so if it's true, so we would jump to PC is equal to PC plus 4 plus branch address. So meaning how many instructions to jump. Like that. Okay, so that is BQ. for B and E. B and E is that if RS is not equal to RT. So PC is equal to PC plus 4. This is because when we execute the branch or any instruction, the PC already at 4. They already at 4. So branch plus branch address. Okay, so basically they are the same with the at the top. Only that the test here is different. They only use different test. Right, so let me go back to the I format. So RS here and RT is to specify the registers to compare. So let's say if A is equal to B like that. So you can say if RS is equal to RT. So A become RS, B become RT. So this is a source. RS and RT become the source that you need to compare. Okay, hold on. Sorry, I don't have voice. Okay, let me continue. Right. What can immediate specify? So what can immediate specify? So immediate is only 16 bits, right? So remember when I said if it's true, if if RS is equal to RT, so here means PC is equal to PC plus 4 plus branch address. Remember? So the branch address is the immediate. Only the branch address here is the immediate. So we only need to know how many instructions that we need to execute after we add PC plus 4. Okay, so the PC has a byte address of current instruction being executed. So we have a PC of content of 040040. Let me look back and at the this one. Ni 00400024. Okay. 00. Where is my pen? 1 2 3 4 0024 like that. Okay, for example. Okay, so the PC has a byte address of a current instruction being executed. So they always plus 4 when they go to the next instruction, right? So we know that PC will add plus 4. So immediate cannot specify the entire address to branch 2. Okay, they can only tell how many branches that they need to jump. So how do we usually use branches? The answer is if you are using if, else, while, or for in your C++. So if else, okay, if x is equal to y, so x plus plus. Okay, so if it's true, we jump to the true statement. If it's false, we jump to the false statement. So how many instruction they need to jump? How many instruction? Let's say we are here. So if it's false, they need to jump to first instruction, second instruction, third instruction here. So they need to jump to the third instruction to go to execute. Like that. So loops are generally small. So typically up to 50 instructions. Usually when we are using if else or maybe while or for your array, so your array also needs this condition that you need to test. So basically in assembly, for looping while and for loop, we also use branches. Okay, when you use the branches, you will need to jump. So usually on C++, they are quite small. So typically up to 50 instruction only that you need to jump. So the function calls and unconditional jumps are done using the jump instruction. So unless you need to go to a certain functions outside of the main program, then we need to use the jump, okay, or JAL. But the rest, we use the branches. So the conclusion may want to branch to anywhere in the memory, but a branch often changes PC by a small amount. So the solution to branches in a 32-bit instruction is we are using a PC relative addressing. So let the 16-bit immediate field to be a sign. Okay, we call it a sign, 2's complement integer, to be added to the PC if we take the branch. So remember, sometimes we jump before the current instruction, or sometimes we jump to the next instruction, like that. So if we jump over the top, okay, so before the current version, so this one means we need to minus. Okay, we need to minus the jump. But if we go down, so we can just add or plus it. Okay, so we plus it. So this plus and minus become the sign. So it will become a sign of 16-bit immediate. So instructions are word. So they are word aligned. Okay, they are word aligned. So the byte address is always a multiple of 4. Okay, because there are instruction in words, which is a 4 byte. So they are word aligned. So byte address must be in 4. So it means that it ends with 0, 0 in binary. So let's say we want to jump one instruction, right? So one instruction means 4 bytes. So we plus 4. Okay, we plus 4. So the number of bytes to add to the PC will always be a multiple of 4. So let's say if you want to jump one instruction, okay, one instruction that you need to jump or branch, sorry. You need to branch to only one instruction, then one instruction that need to jump times 4. Okay, times 4 to add the 4 byte. Okay, to add the 4 byte. So specify the immediate in words. So for the branch calculation, if we don't take the branch, let's say it's false, it false. So we go to the next instruction. So PC plus 4 means byte address of the next instruction. But if the branch is true, branch is true. This one is branch is false. So do remember the coding or the running, the execution of the instruction is line by line. So if the branch is false, meaning don't take the branch. Okay, don't take the branch, then they go to the next instruction. But if we take the branch or the branch is true, then they will tell you that they will tell the PC plus 4 plus how many instruction they need to jump times 4 byte. Because one instruction is 4 byte. So one instruction that we need to jump, say times 4, then that is the number of your immediate. Okay, so observation, immediate field specifies the number of words to jump, which is simply the number of instruction to jump. Okay, so immediate field can be positive or negative. So due to hardware, add immediate to PC plus 4, not to PC. Again, not to PC. Will be clearer while later on in course. Okay, so I'll teach you later on the maybe on the next I think on the next slide. Okay, on the next lecture. Right. So now, okay, we have a branch here. Okay, branch BEQ, register 9, register 0, and then END. So usually when we want to jump, we mention a label. Okay, we always write it in label. So branch equal register 9, register 0. So if we take this branch, okay, if the content of register 9, okay, if the content of the register 9 is equal to 0, then we need to jump or branch to N. Okay, so if true, if true, jump to N. So if we want to jump to N, so we would calculate this is line 1, line 2, line 3, line 4, line 5, like that. Okay, so we count it as a line. So line 1, line 2, line 3, okay, line 4, this is line 4, and then this is line 5, which is N. So the branch format is I format. Okay, look at the green sheet. Branch equal is 4 in opcode. And it is an I format. So opcode is 4. RS is 9. Okay, so this is RS and then RT for the first and the second operand. Okay, look at the table there. So here RS, RT. So RS and RT, register net and register 0, first operand and then the second operand. Okay, what about the immediate? So how do we want to count the immediate? Okay, look at the MIPS code here. Number the line. Okay, number the line. So BEQ start at line 1, ADD line 2, ADDI 3, J loop is 4, END is 5. So when you want to start to count, okay, you go to the next line. So this is the current line, right? So you go to the next line to count. Count is equal to 1. Count is equal to 2. Count is equal to 3. Count is equal to 4. Let's say you have a space line here. You put a line, next line, like an empty line. So it does not count as an instruction line. Okay, so only the line that have an instruction, then you can count it. Okay, you can count it. So next is count 1, count 2, count 3, and then count 4. So number of instruction to add or to subtract from the PC starting at the instruction following the branch. Okay, following the branch. So meaning after the branch, you start count 1, 2, 3, 4. So this is 1, 2, 3, and then N is 4. So we start counting from line 2 because the PC has already add next instruction. PC is equal to PC plus 4. And in this case, the BEQ case is immediate is equal to 4 based on the counting. Okay, so we do that based on the QT stream. So it depends on the, what do I say, how do I say, it depends on the architecture of the simulator that we use. So in order for you to understand how to use the branching here, we refer to the QT stream architecture. So QT stream architecture 9.1, the version is 9.1.20 at that moment. At the moment of the nodes is written. Okay, so in this case, QT stream doesn't add PC plus 4 yet. So we start counting here. Okay, we start counting 1, 2, 3, 4. Okay, but if if you are using on other architecture, other architecture, so the branching calculation might be different. So how do we write the code? BEQ register 9, register 0, and then END, right? So BEQ is 4, RS is 9, RT is 0, and then the number of branching instruction that we need to jump, right? We need to jump 1, 2, 3, 4. So our immediate is 4. So only 4 instruction we need to jump. So we put a 4 here. So we decode it into instruction, binary. Decode into binary representation. So you will have a 6-bit of 000100, and then this is a 5-bit of register 9, 010001, and then 000. And then the 4 here, we have a 16 sign extent of 4. Okay, sign extent of 4 here. So this is your branch machine code. Okay, this is your branch machine code. So for branches, we assume that we won't change to branch too far. So we can specify change in the PC. So for general jump, okay, meaning we don't need to test the condition. No if. There is no if A is less than 0, like that, right? So there's no condition to test. But in this case, we just want to jump. So for example, if you want to jump to somewhere, let's say you want to go to a function, right? You want to calculate average. You want to calculate average, and then you call a function. So you would send a variable like that. So what you would do is that you use a jump. Okay, you would use a jump or JAL to jump to a certain position. Okay, so using a general jump, we may jump to anywhere in the memory. Hence, what we call as a pseudo direct addressing. J format is what we call as pseudo direct addressing. Alright, so ideally, we could specify a 32-bit memory address to jump to. So unfortunately, we can't fit both a 6-bit opcode and 32-bit address into a single 32-bit word. So we need to compromise. Right. Sorry. Right, sorry. So define the fields of the following number of bits each. So for opcode, we have a 6-bit. So the rest become your target address. Okay. So the rest become the target address for your jump. Because the jump doesn't need any registers. Okay. So we only need to provide the opcode to tell, oh, this is the jump. And then where do you want to jump into? So the key concept is that keep the opcode field identical to R format and I format for consistency. So simplicity and consistency to make the execution in a uniform so that the performance is much more better. Okay, so the rest is that we combine. Okay, we only use the opcode, but the rest of the other field is combined to make room for the large target address. So now we have a 26-bit that we can set it as a target address. So in this pseudo direct addressing, the effective address is calculated by taking the upper 4 bits of the program counter and then concatenated to the 26-bit immediate value or the target address, and the lower 2 bits are 0, 0. So in this case, why there are 0, 0 at the lower bits, it's because of when we jump, we always jump 4 bytes, 4 bytes, 4 bytes. So let's say 4 bytes, right? So 4 bytes in binary can be represented into 100. So this 00 is needed. Okay, so for now we can specify 26 bits of the 32 bits bit address. So the optimization is that not just like with branches, jumps will only jump to word aligned addresses. So the last 2 bits are always 0, 0 because of the word aligned addresses, because of the 4 byte. Okay, so now we specified 28 bits of a 32-bit address. So where do we get the other 4 bits? So by definition, take the 4 highest order bits from the PC. Okay, so they will take the first 4 bits. Okay, the leftmost 4 higher order bits on the PC. So since the upper 4 bits of the PC are used, this constrains the jump target to anywhere within the current 256 megabyte block of code. Okay, so 1/16 of the total 4 gigabyte address space. So if you are using a 4-bit of the PC, so the instruction that they can jump is within a 256 megabyte code. Okay, so if we absolutely need to specify a 32-bit address to jump anywhere within the 4 gigabyte space, we can always put it in a register and use the JR. Okay, jump register. It's like a pointer register, but the pointer register contain the address. Register address. It become a register address. Okay, so in summary, so let's say the new PC has an address from 31 to 28. So the first 4 bits is taken from the PC, and then we combine with the target address, which is the 26-bit, and then add with 2 bit zeros. then you get a complete of 32 bits of the new instructions, a new address that they need to jump. So understand where each part came from. So first is the 4-bit from the PC, 26-bit is the target address, 2 bits here is the word align. Okay, 2 bits here is the word align, so that we need to add 2 bits here. So when we combine, we get the 32 bits. So the example, okay, example is we need to have a value of the PC. So where does the PC come from? Here it says the value of the PC is 004000024, right? So you can look at the first column in your text segment. Okay, so this is your content of the PC. Okay, this is the content of your PC. So you can just refer to the Qt stream here. Okay, so as you can see, 0040000, like that. So this is your content of your PC. So in this case, the example use a PC of 004000024. And then they have a loop ADD T1 S3 and S3. And then at the end of a certain instruction, they want you to jump loop. So where do you want to jump? They want you to jump to this position, 004000024. So whereby this is where the loop is. So they will take out the PC, the current PC, the first 4 bits. So the loop target address are 000. This one, this one, okay, is 000. Okay, and then the next 26 bit, okay, the next 26 bits comes from the loop target address. Okay, from the loop target address. So here is 004000024 is we take out and we expand or convert it into binary. So you convert it into binary, so you will get a 004000024. So this is in a binary bits. Okay, so then you would take out, okay, start from the second octet, from the second hex, from the second hex here. So this is the second hex. So 000 0100 until this one. Until this part. Until this part. So until 01. So your 26-bit target address will be loaded here. Okay, will be loaded here. Okay, so they will load it here, the 26-bit to become the target address. And then the opcode. Okay, the opcode is 2 hex. So it will become 000010. Okay, so where does the target come from? The target comes from the where the loop is. Okay, where is the loop? And then we take out the address, the memory address. So 004000024. And then you count from bit 27. Okay, so this is bit 27 until bit 2. Okay, until bit 2. Okay, so this is 31 until 28, if I'm not mistaken. Okay, and then this is a bit 0 and then bit 1. And then this is a bit 2. So bit 2 start here. And then bit 27 start here. So you copy bit 27 to bit 2 to the target address. To become the target address. Okay, and then put the opcode on the opcode 2 on the opcode field. So 000010. So there you will get your machine code for your jump instruction. Right. So in summary, MIPS can be represented into 3 formats. One is R, I, and J. Okay, so if we divide it into a certain fields, you can see the differences and also the similarities. Right, so there are certain only the opcode remain. Only the opcode remain, whereas the others will become different. So branches use a PC relative addressing, while jump use absolute addressing. So this assembly is simple and start by decoding opcode field. So how? Let's say you are given a binary numbers or maybe a hex instruction. Okay, let's say you were given what is the assembly language statement corresponding to this machine instruction. Okay, now you need to become a Neo back again and then try to decode what is this machine instruction. So first count the numbers. So you need to count 1, 2, 3, 4, 5, 6, 7, 8. So now you have 8 hex, right? So 8 hex means 8 times 4 is 32 bit of instruction. So you can consider this is an instruction. Okay. So and then first is that convert the hex to binary to find the op fields and then set the bit based on the R format field. Okay. Since it has the most field available of all format, we don't know what type of format yet. We just divide it based on R format. Okay, because R format has the most field available. So 00AF 8020 is convert to binary, become 000 000 1010. And then 1111 1000 0000 0010 and then 0000. Alright. And then I would write the bits position. So this is 31 to 28 like that. And then this is 27. Okay, this is 26. Okay, 26, 25, 24, 23, 22, 21, 20. And then this is 16. And then 15, 14, 13, 12, 11, 10. I'm supposed to be here. I don't know why. Okay. This is 5. Okay, so this is 5. So 5 should be here. Okay. So determine the operation. Okay, so when I rearrange it, okay, in a 4 bits, and then I would divide it into the field of R format. So we start with the opcode 6 bit, and then 1, 2, 3, 4, 5, like this, and then 1, 2, 3, 4, 5, to get another 1, 2, 3, 4, 5 again, and then 1, 2, 3, 4, 5 again, and then 1, 2, 3, 4, 5, 6. Now we have a 6 bit, 5 bit, 5 bit, 5 bit, 5 bit, and 6 bit. Okay, so determine the operation. Look back on the opcode. If we have all 0, on the opcode here we have all 0, then you would know. If 31 until 26 contain all 0, then and bit, okay, and bit 5, okay, bit 5 here, this one, okay, bit 0, 1, 2, 3, 4, 5, bit 5 here, okay, bit 5 here until bit 0 has a value. In this case, we have 1, 0, right? There's a bit 1 here. So then you should know that this is an R format. So basically, you just look at the opcode. If it's all 0, then it is an R format. Okay. And then convert this function value. This is function. Okay, because of this is all 0, right? So because this is all 0, so you should know that this is an R format. So this is your function. So convert all this field into the equivalent of the R format. So when you convert the function, okay, you can see, okay, when you look at the function here is 1, 0, 0, 0, 0, 0, right? So convert it into hex. So this will become 2, this will become 0, so you will get 20 hex. So look back on the green sheet. So find 20 hex on this column. Okay, on this column, 22, 23. Look at the R format only, only R format. So 0/2A, 0/27. This one. 0/20. So 20 is your value of your function. Then look at the mnemonic here. Oh, it is an add. So look into the reference for opcode and function opcode slash function column with a value of 0/20 hex. So the pattern represents an add instruction. So write on the opcode is 0, and then on your function is add. And then convert. Okay, convert the function, convert the registers here. So this is RS, RT, RD, and then this is a shift amount. So shift amount is always 0, and then this is RS. RS is 5. So what is 5? So look at the register 5. What is 5? Here it says, 5 is A1, A1, here, A1, and then 1111, which is 15. 15 is T7, and then 1000 is 16. 16 is S0. Okay, so I'll just look into the value here. So 16 means S0 until S7. So 16 for S0. So you just write it here S0 and then shift amount and then you rearrange back again. You rearrange to add here, and then this is register destination, right? So you will put it here, and then your source is as the first operand, RT is your second operand. So now you have the full assembly instruction that you have successfully decoded. Okay, so that is how you want to decode your machine language. So once you have done this, so you can try. Okay, you can try for the instruction that you have translate from the exercise given previously, right? So for your own, and then try to decode it. Okay, so I would give you a quiz for that. And then I would ask you how to decode that instruction. Okay, so all type of instruction I will give it to you. So you need to be able to do that. Maybe I will put it inside like a tutorial in the uLearn. I'm not sure. Because of the design. So the easiest way is by writing it on the paper, but because of the time, right? So I'll just use the machine to check your answer. Okay, so I'll try to write the tutorial for that. Okay, so that's it for the lecture. Okay, Alhamdulillah, I'm finishing it because next week I'll see you for the next chapter, chapter 8. Okay, so is there any questions? Apa nak tanya? Okay, for sure, no question. Everybody keep quiet. That's okay. Okay, that's okay. So, Ahmad, I'm not done yet. Thank you, doctor. Okay. All right. So, next time I would explain when you were decoding the instruction, what would happen on the processor. So, let me finish today because of there's too much information that you need to digest later on. So go back, have a rest, and then come back later on to do the practices. So so don't worry. Inshallah. Although the subject looks too robotic for you, okay, but this is only a basic. I don't ask you to create a robot. Okay, I only ask you to create only a calculator. Only that. Okay, so that's it. I'll see you next week. Okay, bye. Assalamualaikum. Assalamualaikum warahmatullahi wabarakatuh. Okay, bye.
Thank you, madam.
Thank you, madam.
Thank you, madam.